Hello, how are you? The last time we met was when I did the MPPT solar charge controller, and this video that I'm sharing with you now is a video on how you can adapt inverter to actually run a refrigerator, also to run sensitive electronic equipment. Inverter output have a smooth wave output, and well, preferably if you would be able to make it produce a sine wave, a true sine wave output. My intention was to actually have an inverter or power supply that would run soldering iron, as I've mentioned on my document. So these inverters, they come in this form, or the other one looks like this, but basically these inverters inside are the same, and there is the basic inside. Let me show you. The inside looks like this, just a transformer here and a driver chip, which is an SG3525 here. I normally would use this board here in what I call the Arduino to drive bigger inverters. I get this disused inverters, get the board and use it to drive a bigger inverter. So they come with this board. It may look different, but the same SG3524 and sometimes 3525, and then a transformer here. The only thing that I don't like about this inverter is the transformer has got aluminium wires. I have done a document on it which will accompany this video, and this document will be shared in my Google Docs, and then also I'll share a schematic of the inverter that I'll be suggesting that you build or you use. So before we begin, as usual, I would like to share with you my philosophy and expectation. So this document, as always, I read it to you on my videos on my YouTube channel, right? So it comes first. Remember, electricity can kill, and then experience in working with electricity is required, and prior knowledge of electronics is also expected. So I assume that you have knowledge of electronics and electrical technology. My philosophy is I always use electronic waste. So the philosophy is to use electronic waste as much as possible. Where you do not have the component, of course you buy new, but electronic waste, those disused equipment that are thrown away, you get components from there and build something that is useful. Yeah, there are always better ways of doing it. So you can adapt and you can modify this design and use it for training or a learning aid, or you can actually use it at home, produce for financial benefit. These projects, I know they are usually sometimes long, and so you need time, you need patience, you need passion to do them, you need dedication. And any comments and maybe feedback and maybe corrections or whatever you want to share with me, there is my email address, tauramirime@gmail.com. Thank you. I hope you enjoy electronics. So what I'll do is I have done I've done this project using my cell phone. So I'll share with you the video clips of what I've done. Where it is not clear, please you can actually email me and ask for maybe clarity. And the points to note, well, there is a document that I have written on this project. This is the document that I have written on this project. So this is the document that I have actually written. and there are basically two circuits. You have the quadrature inverter, which I'll share with you as well. The quadrature, a sine wave generator, and a triangle wave generator compared out here, and then smooth start here for slow start, and then you have your output here. And then the driver circuit is this one. This is the one that drives the H bridge. Use the MJE 13007, or you can use one MJE 1300, I think from 1 to 8. I've tried to use MOSFETs here. The MOSFET will not work very well here. Here is the ULN 2003, and well, basically it's just transistors here. You're actually using transistors here to switch on and off. Though on my inverter the signal here was not good. I don't know why. Maybe I must just use the proper H bridge drivers. Yeah, the signal here was not good. Later on the video also it shows. I'll share with you how it looks like. So here is PJT, here is the ULN 2003. Right, here is a filter capacitor, filter inductor, and here is a feedback transformer. Then output, at the output here, I use a VDR, voltage dependent, or MOV, metal oxide varistor here, to actually protect the equipment over when there is over voltage. So the MOSFET, that's a K160F10, it's a Toshiba MOSFET. So it's not this IRFB. I think well, you can use the IRFB, low ohmic resistance when it's on. The problem that I had was well, like I was saying, the signal when you use a MOSFET, the signal that comes out won't be as good as this. This is the signal that goes to drive the H bridge. Okay, and then also on the transformer I had a problem when I used the original aluminium wire. I had to change to copper, so I had this copper wire, enamel wire, from another transformer, and well, I only took 3 strands from it, around 4 meters, 3 strands 4 meters together, and I replaced the aluminium winding on the original transformer. This original transformer, I mean, looks like this. Well, it was different from that one, but well, the same. Take out this aluminium wire. This is aluminium winding. Take out this one. Of course, leave the secondary. This is the secondary winding. This is the primary winding for the inverter. So take out this one and get the copper winding. LML we can get as new, no problem. 3 strands. Well, don't make it too thick, because well, it's a small transformer. So this transformer is actually a toroid transformer. They also come as the EI transformers, and the same applies. You take out the winding, and you actually adjust the length and rewire. If you decide to use the aluminium winding, if you have soldering equipment for aluminium, I think you can go ahead. I had a problem when I wanted to clamp on the points, so that's why I had to decide to use copper. And then also I'll show you, this is how I designed. This is the triangle generator. I'll also show you that you have to use the FET input op-amp. If you try to use the BJT, it won't with the LM358. The signal is not good. Use the FET input op-amps. I don't know of the MOSFET. I didn't have a MOSFET input op-amp. I had only the LF353 and the TL082, and then the LM358. So the FET inked op-amps, the LF353 and the TL082, actually would produce a signal that you would want. So the video clips are as follows, and they will be edited. Of course, some areas won't be clear. This is a Chinese inverter that I've modified. As you can see, it's running. That's 12 volt input, and then the output 220 volts. Sorry about that video alignment. Okay, right, that's 12 volt input, and the inverter is running, the LED is on, 220 volt, and what I've done is I've actually used the same transformer for the inverter, but the MOSFETs is the MOSFET block. I have MOSFET here, the 160 M10 MOSFET, and here is the IC, that's an SG 3525. If I can zoom in now, you can't, yeah, it's not really visible. That one is the feedback transformer, a small transformer for the feedback. Right, and what else? Okay, the fan is not yet installed. I'll use a temperature sensing circuit to run the fan when the transformer gets hot. It's going to be mounted on the transformer. So yeah, this is the modification. I'll try to run a solar rated fridge using this small inverter. As you can see, that's a very small inverter. Yeah, that's a 10 centimeter diameter transformer, 10 centimeters by 5 centimeter height. Yeah, 10 by 5 centimeter height transformer. That's a small transformer. I want to use it to run a fridge. Okay, right. Nice stable output. Very nice stable output for 12 volt. Okay, 220 volts. Okay. Hello. Now this is the transformer after rewiring. I had to remove 1/3 of the winding, the secondary winding, the thick wire, and it was 8.2 meters, so 1/3 was 2.7, but I removed 2.5 meters, which is this part here that I took out, and then rewound the transformer, right? And as you can see, this is the two ends, and remember, please, this is aluminium wire. You can't solder this one, you have to clamp it. It has to be clamped like the original clamps are here. You can see the original clamps, and this one is the other end that I cut out, so I have to clamp it. I'm going to clamp using this piece here, this clamp here. I'm going to screw and a clamp, so I'm going to use that red wire to clamp it to these two wires. Okay, so let me go on. Okay, now I'm running the inverter, and here's the current meter. I'm measuring current. Here's the battery I'm using. Right, I'm going to be measuring current now. Right, let me switch on the inverter. Right, switch on the inverter. You can see. Okay, for the meter is not stabilized. Now it's stabilized. Right. Okay, and here's the current. That's 330 milliamp. And that's the voltage, supply voltage is that much, 12 volt. Right, hello. This is the fridge that I'm driving with that inverter, that Chinese inverter modified, and this fridge is a solar rated fridge, the DeFi Eco, energy efficient. Okay, and then the energy rating of that fridge is A, and here is the kilowatt hour per year, 263. That's the volume of the fridge, freezer volume. Okay, the model is D5CF300S. Okay, freezer. Okay, South African made. That's an A class. And here's the sound of the fridge running. Okay, that's the sound of the fridge running. You can hear the sound of the fridge running, and the temperature setting is that one. Okay, it has got that temperature setting. The fridge is actually a hybrid fridge. Now you can see this is the solar input. Switched it off. It's running from the inverter, and the inverter that's running the fridge. Okay, you see the inverter. Right here is the inverter running. As before. Okay. See the inverter running. And that's 220. Focus is not right. Okay, that's the inverter running. Okay. That's the inverter running. Right. It makes that sound. It's the sound of the inverter. Okay. 12 volt battery supply. 12 volt, and here is the output 220. Okay. 220 volts. Okay. That's 220 volts. And there is the 12 volt battery level output. Okay, it's connection. Okay, don't mind the high, this high and low. Well, it's no longer working. I took it out. Okay, thank you. This is the inverter that I modified to be smooth wave sine inverter. Right, as you can see, voltage 230. Okay, and then here 15 volts. That's the DC to DC power supply. The green light background is coming from inside the DC to DC converter. Just made it for decoration basically. Okay, then the sound. Okay, as you can see, that's a Chinese inverter SI500VA made by Echo. Okay, show you the inside later on. Okay, I want to show the difference between FET input op amp, the TL082 and the LF353 compared to the LM358. This is the LM358 signal. So I'm going to change the op amp, and you will see how the triangle looks like. Right, now you can see this is the signal for the LF353. Nothing changed on the time base and on the fault per division, but as you can see now the signal is smaller in amplitude, the frequency is now higher, but the signal integrity has improved, much improved. This is what you will be looking for on the LM358 signal. The amplitude was big and the frequency was low, but the signal integrity was very bad. And this, let me change the frequency setting, time based setting so that you see how the signal integrity looks like. Okay, so perfect, nice, perfect signal, though amplitude is reduced. Okay, the signal setting is at 2 volts per division, and the frequency, the time setting is 50 microseconds per division, and that's the signal there. The graduation, I guess you can see there, and you can calculate the frequency there. Okay, right, that's the graduation. Maybe we can calculate the frequency from there. Okay, let me change the position a bit. Okay, the power supply to the circuit is 15 volts. Okay, and that's the circuit here. Okay, just zoom it a bit. That's the circuit there. The scope probe here, and the power is here. Okay, and that's the power supply here. The power supply voltage there. Okay. Okay. I've just made the 10 per division to that's okay, right, that's 20 here. That's 20 micro. The dot is there. Okay, and it's not that visible, but it's at 20 there, 20 microseconds per division, and the signal, we get a reference point here. Okay, from there, from that point here, going up, down, so that's 20 microseconds, 20 and a half, that's the 30 microseconds. For the cycle, that's 30 microseconds for the cycle. If you wish that you take the rising signal, okay, from that point here, that's 20 and a half there. So this is the one cycle, bam, there to there, right? So that's 30 microseconds for the period. Okay, 30 microseconds for the period. So you can calculate the frequency there. Okay. Okay. Now for the LM358, that's the signal. As you can see, same volts per division and same time per division, 50 microseconds per division, and here 2 volts per division. Okay, right, the slot is there. Okay, right here now, so you see signal here. You can take reference, and we just try to adjust so that give a reference there, so you can see. Take a reference here from that point here to that point there. Okay, so that's 50, 100, 150, 175 microseconds per cycle. Okay, 175 microseconds per cycle for the LM358. And the voltage, that's the reference point here. Voltage is 2, 4, 6, 7 peak. So the peak to peak will be 15 volts. Okay, it's clipped here. That's clipping, and here also is clipping. If I zero it, you can see 0 point. You can adjust the 0 point here. So it's clipping, right? But that's about 7 volts amplitude. Okay. Hello. Yeah. Now this is the output of the quadrature sine wave oscillator. As you can see, right? We have a 4-volt peak signal, nice sine wave, frequency. Let me show you. That's a frequency 85 milliseconds per division time. That's 5 milliseconds. The timer is here. 5 milliseconds per division. So we have from here 5, 10, 15, 20, plus minus an error there, which is more, and the voltage is 2 volts per division here. It's 2 volts per division. Okay. We have 2, 4. So we have 4 volts, which is equal to the triangle wave. They should be equal, so that you are comparing equal levels. So that's how the inverter is actually designed. Thank you. Okay, signal from the inverter. That's the pulse signal. You can see there's no cap here. There are many pulses there. You can see, and a good scope. Okay, let me just increase the frequency. You can see this is pulsing signal. Okay, the pulses. Okay, pulses here. Just changing time per division there. Okay, the high side MOSFET drive signal and the bipolar transistor. Okay, looks like that. Not stable, but that's the stable. Okay, the lower side MOSFET drive signal. That's where the problem is coming. Not so nice, dome shaped, and not very stable. Okay, increase voltage per division. Looks like that. Okay, that's that nice. Okay, looks like that. Voltage per division. Stable. Okay, now this is what I have done. Instead of using the original aluminium winding, I've taken out the aluminium winding and replaced it with copper. So this is now copper. As you can see, this is copper. Okay, the inverter is live now, so it's not advisable to use a metallic screwdriver like this, but I'm just pointing out. So this is the winding. I've used the three strand copper wire from another transformer. It was a transformer that I stripped and adjusted the voltage. It was a big transformer, 3 kVA transformer. So I've taken only 3 strands, 4 meters long, and I've used it to rewire the transformer. So it's now running using copper, and this is the circuit for the smooth wave generator. Okay, and this is the DC to DC power supply, 15 volts, 12 to 15 volts constant, and here's the fan running. Okay, I have not yet put a controller. It's running continuous. The moment you switch it on, the fan starts to run. I've used copper because the clamping was not good. It was hitting on the clamping points, so I had to change to copper so that I can solder. I guess there is a way of soldering aluminium wire to copper connections. So the inverter is running. It's now quiet enough, and the reason why I changed the driver circuit is because the modified square wave was making a lot of noise, so I had to use the smooth wave generator to run the inverter. And this is the power block. The MOSFETs are clamped under here. They're clamped under here. You can see the clamps there. These are the MOSFETs clamping. The ULN 2003 is here. The driver, and that's the bipolar transistor there for the high side MOSFETs. Okay, the input capacitors are there. This is the output capacitor, and if you can see, yeah, that's the output inductor here for the filter. So that's the inductor for the filter. Okay, let me just zoom it properly. Inductor for the filter with that capacitor here. That capacitor is 0.68 microfarad X2 capacitor. Okay, and that's the transformer for the feedback. This transformer here is for the feedback. Okay, right, and that's the battery I'm using there. The T105 RE Trizone, two of them, 212, each is 6 volts. And so the two to make it 12 volts. That's the output here. Okay, 220 volts. Yeah, 15 volts. That voltage is coming from the power supply, the DC to DC converter. That voltage is not the battery voltage, it's the DC to DC converter voltage, 15 volts. That's the power supply here. That's the voltage it is giving out, this one. Okay, right, so this is the battery voltage here. 13.9 volts battery voltage here, measured here on these terminals here. Battery voltage, okay, 13.9 volts. Right, you can hear the sound. That's the sound of the inverter running that fridge. Okay, right. And here's the feedback circuit, the LED and LDR, okay, and flag covering. Okay, right. One other thing that I did not mention is that this transformer here runs quite hot. I can touch it though. I can touch it, but I can't do this. It's quite hot. Yeah, here's the fan. Okay, the MOSFETs is quite cool. MOSFETs are very cool. Okay, very cool. I've used the K160, I think 160F10 is a Toshiba MOSFET 2 milliohm drain to source resistance. They're quite cool. I can touch without a problem. I don't like aluminium winding because it's not as good as the copper. Okay, of course the primary side for the inverter is copper, like used copper, but the secondary is still aluminium, original aluminium winding. Right, now the inverter, here's the last design, here's the sound, very quiet, only the fan, nice and quiet, easy. Okay, I took out the inductor as a full filter, just a capacitor. It's now quite easy.